He is a distinguished scientist and honorary professor at the Solid State and Structural Chemistry Unit, IISc Bangalore. His pioneering research focuses on strongly correlated electron systems and semiconductor nanomaterials. For his contributions, he was awarded the prestigious Shanti Swarup Bhattanagar Prize in 1994. He is elected as a fellow of all the three Indian National Science Academies, as well as the fellow of the American Physical.
Thank you very much.
So today he's going to speak on this topic: what drives the bond disproportionation in the rare earth nickelates?
It's a wrong place to even pretend to be pretending. So I'm going to talk about this particular topic, and it will become clear at the end why I have chosen this particular topic. But before I start, I'm, of course, extremely honored and grateful to the organizers for inviting me to take part in this extremely and extraordinarily special event. And even if you did not invite me, I would have gate crashed. TVR is very special to all of us. And there's no way I'm going to miss, we fondly call him TVR. Because thank you, TVR, for being such a teacher, a mentor, an inspiration, and a friend that you've been to me, like many others in this place, I'm sure. There'll be more occasion on the day after tomorrow to talk more about anecdotes and incidents that I very fondly remember from my very early days, from my student days, and then on, which maybe I'll have a chance to talk about. But I must wish happy 85th year. He is not yet 85 years old. That will be in August, way off. He's a very young man. Don't call it the 85th birthday. That is another almost a year away. And best wishes for many more happy and healthy years filled with exciting science and inspiring all of us. Okay, so what I'm going to talk about today is actually done by this brilliant series of students from S.N. Bose National Center for Basic Sciences, led by Priya Mahadevan. So it's been many generations of students who have contributed to it, which is, tells you that it's an old wine in a new bottle, which is the best way of doing it rather than doing it the other way around of doing the new wine in old bottles. This has been a long time in the making, and it's been very effectively also contributed by two other people, Cesare Francini from Vienna and Andy Millis from Columbia. And that's why you see the acknowledgement to Indo-US that brought in Andy into this framework of the work that you did, and Indo-Austrian that brought in Cesare. PI is supported by Serb Power, and our activity is very generously supported for the last 4 years by this national fellowship that has kept us going. There's the results that I'm going to talk about is in an archive, has been put there recently. And all of you know about nickelates. In fact, I'm thankful to Tanushree for reminding everybody that 3D materials exist. They have chemical formula, and they have structures. And somehow these things may matter in some of the cases, and nickelate is one such case. And that's why I thought I have to belabor that point, but thanks, Tanushree, for having covered that aspect. This is the phase diagram of nickelate. When I talk about nickelate, I'm talking about a general class of compounds. Ln is not an element for the students. Don't look for it in the periodic table. You'll not find it. It's a generic name for the lanthanide series that starts with lanthanum, ends with lutetium. There are 15, if you include lanthanum also. It's an F0 system. And you can make this compound with all those elements here from lanthanum to lutetium. They'll all form in this very celebrated structure called the perovskite structure. I'll not talk specific about the structure, but the structure is underlying everything that I'm going to talk about. It's a cubic structure, essentially a cubic structure, where nickel is surrounded by 6 oxygen, making an octahedra. These octahedra form, corner shared, linking in all dimension, giving rise to the 3-dimensional structure that I'm talking about. Why people were interested or excited about nickelates? It was that they found at one stage that they show some very interesting phase transition, and this is the phase diagram constructed for that. And the phase diagram here is the phase transition temperature marked, and I'll tell you in a moment what the phase transition we're talking about. But here is an axis label that you may not be familiar with, which is called the tolerance factor. Think of it, this tolerance factor, as the size of this lanthanide ion. The lanthanide ion, as you go across from lanthanum, which is rather large, go towards lutetium, it becomes smaller simply because the inner potential, the nuclear charge is increasing as you go across the periodic table, contracting the 4F level and the S level and the D level, everything. And therefore, the size is decreasing as you are going that side. So it's the size of the rare earth ion that's controlling somehow the phase transition, because you can see that the phase transition has this particular shape.
They still form in the same structure.
They form in the same structure, modulo some changes in the distortions, but they're all in the perovskite structure. And we are going to talk about that genetic aspect without going into the details of the small changes in the distortions that happen across the series. But you can get to that. You'd also notice another abbreviation here, CO, which stands for charge ordering. What we mean by that charge ordering is that, incidentally, the interesting part, let me tell you, is this charge ordering phenomena, you can see happens for all of them, praseodymium to lutetium, but does not happen for lanthanum. It's going to be one of the central questions that you're going to ask. Why does it happen for every lanthanide? What's wrong with lanthanum? The entire series is named after lanthanum as lanthanide, and yet it is not able to show that phase transition. This phase, the white part of it, is always metal. So at high temperature, these ones are paramagnetic metal. Lanthanum nickelate remains metal all the time. If you lower the temperature for any other lanthanide, it gets into an insulating phase. This is the insulating phase that it gets into. But it has a very peculiar insulating state, which is known as the charge-ordered state. And let me explain what charge ordering is all about. What do we refer to? What do we refer to, first of all? This chemical formula that I have told you, we need to understand a little bit that oxygen donates or accepts 2 electrons from the system. So it has a 2- 2 excess electron charges comes on top of the atomic oxygen. So it has a 2- charge. Where do these electrons come from? Because I need 6 electrons. There are 3 oxygen, each taking 2 electrons extra. Where do they come from? 3 come from the lanthanide. So 3 more must come from nickel. So nickel donates 3 electrons, and that makes nickel into the D7 configuration. So that's very important to keep in mind. And the idea is that if you take 2 of this nickel 3+, if it happens to spontaneously arrange itself by transferring 1 electron from one of the nickel 3+ to the other one, then you'll end up with a nickel 4+ and a nickel 2+. And if it happens in an ordered manner, you'll get this charge ordering, where at each of the lattice side, going in any of the 3 directions, you'll find nickel 2+, nickel 4+, nickel 2+, nickel 4+ in every which way. And the system becomes charge ordered. This kind of ordering always promotes insulating state, and the idea was that this charge ordering is responsible from going from the paramagnetic metal to the charge ordered insulating state. So this is a basic consideration that we need to keep in mind. But one thing is for certain, that experimentally we never measure charges. Charge cannot be measured. It's not even a quantifiable object. There are, Senthil, any question? There is an idea that here, originally it was thought to be Pauli enhanced. And on this side, I have more Curie-Weiss-like behavior in magnetism. But there are now, magnetism in these materials are still being debated. This is also has Curie component in it. So I would, for the purpose of this talk, I'll completely ignore the dashed line, so it is not there. Yes.
Will you do XPS to charge?
Every experimental measurement that claims to measure charge measures the charge that is defined within itself. You can do it many different ways. You can do X-ray absorption, you can measure some charge. You can do an XPS, you can have a notion of a charge. You can do DFT calculation and do some kind of partitioning of the volume space and calculate some charge, but these charges don't agree with each other. And particularly the calculation where you have a more or less well-defined prescription of how to calculate charge, you'd find that there's hardly any difference between these two, if you did that. And if you do a measurement across this, you will find some minor changes in the XPS, let's say, core level spectrum. Of course, you'll have a drastic change in the valence band because it goes from metal to an insulator. But in the core level, the changes would be more related to reflect this change from metallic state to the insulating state in terms of screening rather than in terms of charge.
Charge distribution should change.
I'm coming to that. Yes, charge distribution
So-
will change in some way, but
Or the pole splitting, I mean, some other ways of measuring.
but I don't know. I mean, there's no obvious way of measuring the charge. One could say that magnetic moment, look at it and try to conclude from there. That's how one of the possibilities is to do that. But magnetic moment also, the nickel 2+ and the oxygen contributions could come together. They're coupled together. You cannot separate them out. So what you measure at the end is some kind of a magnetic entity that's living on the cluster of nickel oxygen at the best approximation of a local description, not on the atomic side. That's what I'm trying to say. Because most of the charge density is between the charges that we're talking about are between the two bonds. Right? So that is what we're trying to say. Okay? So that's why I said that we never really measure charges. Something that we measure and we know very well without any dispute or controversy is bond lengths. And that bond length behaves in a particular way when you go across this transition. How does it go? And in fact, that leads to the name that is now more accepted than calling it charge ordered, and that is called bond disproportionation. And let me explain to you quickly what I mean by that. To start with, in the paramagnetic metallic high temperature phase, if you look at the nickel and the oxygens around it, I told you there are 6 oxygens around. There's a corner shared oxygen with the next nickel, and these nickel oxygen distances are all equal. And that's about 1.95 angstrom there. So all the bond lengths between nickel and oxygen are identical. But in the lower temperature insulating state, very strange thing happens. What happens is that there's a breathing mode. Around this nickel, suppose, all the oxygens come closer to it. Since nickel-nickel distance doesn't change, this one shifting that way makes this nickel-oxygen bond shorter here, but this nickel-oxygen bond longer. So now we have a bond that is alternating, short, long, long, short. It goes on that way. Bond length, which was uniform, homogeneous here, now disproportionates into a short bond and a long bond and a short bond and a long bond in all 3 dimensions. And so we call it the bond disproportionation that takes place. And that does not lead to charge disproportionation. In fact, one of the manganite that also we had looked at, again in terms of calculation, DFT calculations, where you find almost identical charges. Charge difference between the 2 disproportionated sites are in the order of 0.1 charge only, 0.1 or 0.2 at the most. Anyway, what we need to keep in mind is that how much is this bond disproportionation? So that is measured by how much does the NIO bond length changes. It was about 1.95. It has become 1.9 or 2.0. So delta NIO is about 0.05 angstrom. And divided by the bond length, which is 1.95. So there's a 2.6% breathing mode changing this long, short arrangement. And that is what we need to keep in mind, because that will play some important role in judging between different models that can be there. Okay, having said that, magnetism I'll not spend time on. It's still a controversial object. It's a very complex magnetic system. One of the simpler way of talking about it is that in the pseudocubic direction, for example, you have up, up, down, down in this direction, in the up, up, down, down in this direction, and also up, up, down, down in this direction. And that gives rise to the basic magnetic structure. In this theme of up, up, down, down, you can have a collinear or a non-collinear arrangement. And here you would find that I have marked 2 different kinds of magnetic sites, nickel sites. This one with a larger moment is associated with the nickel 2+, and the one with the smaller moment is nickel 4+. The nickel 4+ is the one associated with the shorter bond length, and nickel 2+ is associated with the longer bond length, simply because the number of electrons are different. And so the ionic size of nickel 4+ would be shorter and nickel 2+ would be longer. Okay, so the question that you are going to ask, what drives bond disproportionation in these compounds? And we will also then, if you have to understand that, we also have to understand why that, whatever that is, that drives it, does not do it for lanthanum nickelate, if it is all such related compounds. So another thing, interesting thing to note is that these nickelates seem to be unique. neither the cuprate nor the cobaltate. And why am I talking about cuprate and cobaltate? Nickel sits in between copper and cobalt in the periodic table on the two sides. For example, neodymium cobaltate or any of the lanthanide cobaltate do not show the bond disproportionation. So there's something very unique about nickelate in this case. So one also wants to know what is so unique about this. So first thing one would like to know, because what we are going to show is electronic structure calculation, and from there whether we can understand what is going on, is that whether this basic distinction between neodymium nickelate and neodymium cobaltate is captured by the kind of electronic structure calculation that I intend employing in understanding this question. And then what we do at DFT is good for that, is to do total energy calculation. So you take the experimental structure, you geometry optimize it within DFT, as good a calculation as you can do, and look at the total energy of different systems and different configurations. You can do the calculation for neodymium nickelate in the paramagnetic metallic state geometry, and in the bond disproportionate at lower temperature, you find that the lower temperature bond disproportionated solution is the lowest energy configuration by 42 millielectron volt. So for the nickelate, the electronic structure calculation does describe the ground state correctly, at least. If I do exactly the same thing for cobaltate, without knowing why it happens, we know that it gives the bond disproportionated solution to be much higher in energy. So bond not disproportionate, homogeneous solution is lower energy for the cobaltate. Again, compared to the bond disproportionated state. So here what we are doing, the two total energies we compute, one for the bond disproportionated, one for the not disproportionate, and look at which has the lower energy.
Both are locally stable.
Both are completely stable solutions. And here we find that indeed, as experiment tells me, this is the lower energy solution. And as experiment tells me, this is the higher energy solution. So that far we have got it right. So that now we can go into the innards of these calculations, trying to answer what gives. So, but I can first ask, so what changes between these two? And what changes between these two can be extracted in terms of the basic electronic parameter, which from DFT I can calculate the hopping value, I can extract the sort of orbital energies, which essentially will give me the energy difference between the oxygen P and the nickel D state, the charge transfer energy as we call it. And this is something that we had looked at in the LA-MO3 series many, many years ago, 1996, when Priya was herself a PhD student. And what we found that the basic things that change, these are the hopping interactions as I go from across the transition metal series. Here is cobalt, here is nickel. Basically, the hopping strength is uniformly decreasing, presumably because the d orbital gets more contracted as I go across the series. So there is a contraction reflected in the decrease in the hopping interaction strength. But more strongly, more pronouncedly, what changes is this ED minus EP. You can see that it changes very rapidly over almost 5 electron volts as you go across the series. So the dominant electronic interaction that's changing is this charge transfer energy, which will denote by delta very often. And it suggests that delta by T is really setting the scale in this problem somehow, so that we'll be focusing more on delta over T across the series or in the various forms of the nickelate that I'm going to talk about. That's how we are going to attack the problem. What do I mean by that, and how do I connect these numbers that I'm extracting from single particle calculations to many particle calculations, or at least the broad description of the many electron calculation picture of simple transition metal oxides? I fall back on the well-known Zanensky-Allen phase diagram, where basically the shaded part corresponds to, these are the single particle excitation spectrum of a many-body system, so that I can map it onto the single particle calculation that I'm doing. These are the one electron extraction removal spectrum. There's the Hubbard band, lower band. There's oxygen P of the oxide. And this is the one electron addition or empty states counterpart, upper Hubbard band. They're separated by Coulomb interaction strength as it should be. And the energy difference from here to here is what the charge transfer energy is. In absence of any oxygen P bandwidth or D intrinsic bandwidth and TPD switched off, that would be the exact charge transfer energy from the center of the oxygen p band, that would be the p level, to the unoccupied part of the d level, and that is how I define delta. There are two limits, of course. There's the Morthaber limit, there's a charge transfer limit. I'll not deal with that because that's irrelevant while you are discussing about nickelates and cobaltates. So we'll stay always in this domain and talk about the electronic structure and its evolution. So how people have, we're not the first one to worry about it. It's being worried about ever since it was discovered in early 90s. And one of the early attempts was from Mizukawa, who did essentially Hartree-Fock calculation on a model Hamiltonian and showed that if you make this charge transfer energy negative, what we are seeing is if these lines, these are some kind of relative, it's a total energy difference. Basically, it's saying that if you go below zero, the system will be in this charge disproportionate state. And that is something you can see that if they do find if charge transfer energy became negative, they find that the charge ordered state, two different kind of charge ordering they talked about. Let's stick with this. This is the more realistic one. Charge ordering on the metal side, it does become charge ordered. There are two calculations they presented, one without tilting, one with tilting, as TVR was asking. There are some twists in some finer refinement that we need to think about, worry about. There are twists of these octahedra. They don't remain in the ideal cubic state, but for the time being, we'll ignore that. And as you can see, that even in these two calculations, the behavior is almost the same. No, this is the charge ordering in the oxygen side, charge ordering at the metal side. And I'll not get into that because it is a starting point of the self-consistent calculation of the mean field calculation. It ends up with something which has still charge ordering substantially on the oxygen side. Okay. But I think what we need to look at is really the MCO part, but they're more or less the same behavior. What I would like to draw your attention to that the negative charge transfer energy that you need to become charge or bond, that's completely unrealistic negative value. That is just doesn't explain anything. Not only that, it doesn't say anything about why LNiO3 is not. For LNiO3 in this diagram to become non-charge ordered, that means it has to have a larger delta. That means it has to lie on this side. And at the end, I'll prove to you, if anything, not if anything, it is. Lanthanum nickelate has a lower charge transfer energy than all other nickelates. So it's even wrong. I mean, there's no way you can put lanthanum nickelate on that side. Lanthanum nickelate will be more on this side, and so it doesn't say why it is not charge ordered. So that remains as a puzzle. Okay. In fact, they also realized that the delta was very large, negative. So they fixed delta at -1, and then they said the breathing mode energy that they were missing out, and they had not, the earlier calculation is, that's why I said charge ordered, not bond disproportionated. They didn't take the breathing mode into account. Now they did a calculation at a fixed delta of -1 electron volt, which may be somewhat more realistic, and asked, how does the breathing mode distortion stabilize that bond disproportionated or charge ordered state? What they found that, yes, they do get, again, this 0. These two data points are where you have charge ordered bond disproportionated state. It's bond disproportionated by hand because this is the distortion that they have given, the breathing mode distortion. But remember, I had told you what the breathing mode distortion is in the real system. The breathing mode distortion in the real system is about 2.5%, and that's out there. Yeah. Yeah, so you have to, first of all, the elastic energy is not part of the calculation in a model Hamiltonian. That is not part of it. It's only the electronic part. And that's why it will be very asymmetric. And that would have a large component, of course, which is completely missing here. So we will not go there. But the point is that within this also, if you take the realistic bond disproportionation, it will be actually not bond disproportionated. And in, yes, that is, I was hoping to avoid that question altogether. The reason being, the physics of charge ordering does not seem to depend on magnetic ordering because we have a charge ordered paramagnetic state. also intervening between the antiferromagnetic state. And everyone, them, us, we love ferromagnetic structure because the antiferromagnetic structure has 160 atoms per unit cell. And I can get away with a ferromagnetic unit cell, which will be only 20 atoms, making all things possible. Now, does it make a tremendous difference? We're saying it doesn't. We're right now trying to do a sort of a representation of a correlated or local moment paramagnetic state a la Zunger prescription for getting a charge-ordered bond disproportionated paramagnetic state. That will be the best one to do because we can get away again with a smaller unit cell. And that is what we're trying to do. We believe that the magnetic ordering is not central to the equations that we're asking. And you'll find that within the ferromagnetic calculations, we'll show that we get all the results correct, or else I wouldn't be presenting it here. Okay, there's also, Igor Mazin had talked about the difference between Jahn-Teller, and Hund's exchange. I'll not go into that. I mean, basically nickel 3+, nickel 3+, if you have, bond not disproportionated, identical, because of you can get a Jahn-Teller stability coming, which is given here. But if you do the hopping, charge ordering, then of course you pay the Coulomb interaction, but you gain the Hund's coupling. That is never negative, so this will be positive, but then there is this breathing mode stability that you can also gain. And so the proposal was that this might be winning over that to stabilize this at low temperature. But again, I'll not go into that. There are other things. So let me tell you our version of the story so that I don't run out of time altogether. So as I said, that there is a distortion of about minus delta and plus delta. And first, do we capture that aspect? So what we are going to do again, total energy calculation, by changing the delta continuously from 0, which is the paramagnetic phase with no bond distortion or disproportionation, and systematically change that and see where it minimizes. And we find indeed it's between 0.04, 0.05 around here that I get the minimum energy, which is the experimentally correct point. As I told you, the bond distortion is about 0.05 angstrom. So we seem to get that right. That gives us some confidence, and then we go ahead with those calculations. As I also said, that the next thing is that NdCO3, NdNiO3, or looking at the transition metal series, as I said, that the controlling parameter seems to be the charge transfer energy, scaled, of course, to the hopping, which I'm just throwing out as a unit in the energy scale. So it's a charge transfer energy that we need to worry about. How do I investigate the charge transfer energy of a given compound and its consequence? So what we do is a twist on the DFT calculation, and this is where Cesare Franchini become a critical partner because they are the generator of these fantastic first principle programs. So VASP, there they rewrote the code to be able to put in a constant potential for the nickel D. And we can tune that by hand as we want, pulling the D down and changing the this charge transfer energy. And that's what we did. And so what we are going to do, you have already seen, this is the upper Hubbard band, and there's the oxygen P. There's a low Hubbard band out there that I'm not going to worry about. And I'll switch on a D, continuously pulling this down and ask the question, what is the ground state behavior of that, all the way when it gets in there, where delta becomes small. But remember, delta is still positive at this point because delta is measured from the center of this to that. And I'll come to this point in a moment. But the reason we want to get to there is now the holes begin to reside also in the oxygen P orbital. And we believe that would give rise to a qualitative difference to the underlying electronic structure, and that's a question we're asking. And this is exactly where connection to TIFR would come about in a few slides down the line. It will lead to an insulator, to bond disproportionate insulator, and further down a metal. And this is exactly what with TIFR you had found out way back in 1992, and I'll show you the results. But we didn't know about disproportionation at that time. Okay, so what we are plotting here, we take NdNiO3 as the experimental structure, and we tune the D level by adding this extra potential and figuring out what the charge transfer energy is by analyzing the results, by mapping it onto some tight binding model. So here, and then we extract the delta effective. Now, delta effective, allow me to go back one slide, is this quantity. Delta effective is actually the one that measures exactly where I begin to populate the top of the oxygen P level. For us, and from our experience with the work that we have done with TV a long time back, delta effective is the right descriptor rather than delta effective. Of course, in the limit of bandwidth going to 0, delta is equal to delta effective. But there is no material in the world where the oxygen P bandwidth is 0, and it makes a critical and qualitative difference between delta and delta prime. And that is what I'm trying to point out to you. Okay, so it's the delta effective. And what we find is that exactly around delta effective 0, there is a transition. This metal is because we have taken ferromagnetic state, antiferromagnetic state, 1 point calculation we have done, and it becomes insulating. So we know. So this is essentially a correlated antiferromagnetic insulator here, and we get this bond disproportionated insulator below 0. The moment delta effective becomes less than 0, the system prefers to break up into bond disproportionated state, with 2 different bond lengths shown over here drastically, and 2 different magnetic moments also. But if you make delta effective considerably lower, it goes into a homogeneous metallic state. Now the question is, how does lanthanum nickelate? Here is, I'm only talking about neodymium nickelate and artificially changing its charge transfer energy. How does it happen? What happens in lanthanum nickelate across the series? Across the series, if I extract the delta effective and ionic radii, which is the tolerance factor, lanthanum is sitting here with a very low delta effective, negative delta effective. And these as a group is up. Incidentally, for all of them, delta is positive, not negative. But delta effective is negative for all of them, and lanthanum is drastically negative. And in the previous phase diagram that I showed in the previous slide, the large negative delta makes it homogeneous metal. And these are in the charge-ordered insulating state. Are there other examples, or is it only nickelate? I'll very quickly go through. We also know strontium iron oxide and calcium iron oxide. Strontium and calcium are supposed to play no role, but this is a homogeneous metal, and there's a bond disproportionated insulator. And I'll show you immediately within this calculation, it's supposed to have this bond disproportionation, this one, and not this one. What we find that the delta effective of SrFeO3, the homogeneous metal, is much more negative than the calcium iron oxide. And this is also negative. So this negative value makes it disproportionated, and when I decrease that further, it gets into the metallic bond state. Is it only transition metals, oxides? No. You go and look at the other systems where Chandravarma had this missing valency paper long time back. All of them have negative delta, effective delta insulators. All of them within this. So it looks like that it's a universal behavior. The moment you try to dope the ligand band, the broad band that exists in the system disproportionates into bond disproportionated insulating state rather than getting into the metallic state. That brings me to why I chose this one. It's a long time back, 1992, this paper that you had published in Promenade. Everything in those days that got rejected from PRL, one got into Pramana. And we had struggled this for a long time there. What did we do here? Forget about the title. Actually, it's all about transition metal oxides, and how to think about transition metal oxides is what it was. This is the ZSA diagram I had shown you, very celebrated Zahn-Sawatzky-Allen phase diagram. What I would like you to see there, it's a U and delta, charge transfer energy. And what I want you to see, the delta equal to 0 and R, that's always metal. In fact, it becomes metal even before, according to them. This is the line that separates metal to insulator in that diagram. The work that we did with TVR, the delta negative is what we had called covalent insulator, later on popularized as negative delta insulator. And this is covalent insulator stage, which is distinct from there. And this is only possible if you do the calculation. Here, the calculation was done actually for a cluster, and this was done for a periodic system, of course, with a mean field approach. And the other distinction that you had made at that time to say that delta is not the right descriptor, delta prime is the more important one. Krishnamurthy is also party in this crime. So any questions can be directed to them. And So it's a lovely work, but often this negative delta insulator has been attributed to this paper, which was published about a year earlier than this particular paper here, that called it negative charge transfer energy in a particular case in a CO2. Without getting into much discussion, the point is that there was another paper another year earlier, exactly 1 year earlier, that had already presupposed, and actually since we knew the phase diagram, we were only struggling with PRL from that time to publish, we had already published that exactly how this negative delta insulator generates. It said that in this situation, if you didn't have the hopping, a small delta compared to the ligand bandwidth, meaning the delta effective, will be metal if you have very small hopping. But if you have a large hopping, then it will split out and open up a gap. I'll just take a minute and open up a gap, forming this covalent insulator, which 1 year later was called negative delta insulator, and that has stuck. The primary differences, these are the two ZSA identified description of the transition metal oxides, this being the Motthabbird regime, this being the charge transfer regime. Together with Krish and TVR, we had identified this covalent insulator regime and this PD metallic regime that, of course, existed in earlier. Our claim is LaNiO3 belongs there, internickelate belongs here, and essentially you can see what happens as you keep pulling down delta. This is a charge transfer limit where U is greater than delta, so this one is irrelevant. Delta effective is greater than 0. You bring it down to the transition point where delta effective is exactly equal to 0. You go into negative delta effective. As long as you are above a critical point, the system spits out a level there, and you get a bond disproportionated insulator, and then you pull it farther down, you get delta effective equal to delta C, which is measured by this now coming and contacting on top of the oxygen P band. You get a metal transition, PD metal, and it's almost obvious to me that this should happen. And this has been realized in the case of nickelates and all other bond disproportionated cases. So my concluding remark, I'll not spend time on that, except for the fact, why did I belabor this particular point, except also, of course, because it's an honor to be showing something that is fructified after so many years, that was started together with TVR and Krish, is to point out that what we have shown from calculation is an universal behavior and a small parameter trying to excite all the great theoreticians here, because I believe there should be a theory of this. Because you have a small parameter and a universal behavior, this is crying out for a theory to explain this. And with that, I'll end my talk, thanking you for your attention.
Questions, please.
TVR first.
About this bond disproportionation, there is a temperature above which there is no bond disproportionation. That temperature, the energy connected with that temperature is much, much lower than the energy difference. So I was just wondering whether there are
Not quite, because the energy differences that I was showing you, of course, of slightly different cases. Let's take the NdNiO3. That's for 4 formula unit. So 45 divided by 4 is in the order of 12, which is below room temperature. So the temperature scale is not really very wrong. I'll not, of course, push it to actually estimate, because the energy difference is not the energy of the transition, but it's in the right ballpark. Because 45 MeV difference I showed, divide by 4. So per unit cell, it's about 11. 11 MeV is about 140 Kelvin, which is uncomfortably close to the transition temperature.
Yeah. I was just curious that if you have a ligand hole, it will show up as a pre-peak in your oxygen Ka spectrum. So is there a way to really look at systematically, among different lanthanide nickelate, that how does this pre-peak varies?
I think oxygen 1s would be the best one,
Yes.
because everything else will have complication. Nickel L23 will not do, nickel K will not do.
No,
So
it's
oxygen
oxygen
Kh will be the best possibility. I should dig into our own data from 90s. We had looked at all these oxygen edges. I'm not too sure how it is, but the cross sections would have very strong effect. What do I mean by that? That oxygen cage also would be very strongly contributed by immediately the states that I'm not showing here,
Right.
which are just beyond this split off state that I'm showing you,
Of course,
which
it
have
will be-
huge cross section. So it'll be really a so I shouldn't answer without looking at the data because it'll depend on the splitting,
Yes.
width, and the resolution of the technique,
Yes.
whether I can see it or not. But it's a very interesting thought, and I should
Sure.
look at it.
Okay.
Vijay here. Thanks, Didi. It's a great talk, actually. I have one question. There are two viewpoint is going on in this field. Is that in nucleates, whether the ground state is completely governed by the strong correlation, the dynamical correlation is important, or other part is the correct magnetic structure, which can be easily done by the DFT. So what is your take on?
These are all strongly correlated. One thing that I didn't talk about, and this is we discussed in this 1990s paper very well, also in discussing NSCO2. The particular one, NSCO2, where the first negative charge transfer energy title came in, actually happens to be a non-correlated system. It's a completely band insulator. It's as boarding a band insulator as possible. In fact, we had shown that even if you made delta minus 40 electron volt, it will still remain an insulator. So it's a just plain simple, but all the nickelates are necessarily strongly correlated system. What we are showing is that the underlying electronic structure on which you have to build your strong correlation physics. It is not to say that strong correlation is not important. That's why you also try to connect the electronic structure parameters that you're extracting to this ZSA diagram, which is the simplest many-body representation of the excitations in the spectrum that can talk about metal and insulators.
So I guess this question will reveal my complete ignorance about these materials. So can you tell us why they are interesting? Is there some technological application of these materials?
Well, first of all, I thought I'll never hear such a question from a great theoretician. Technological implication is the need or necessity prerequisite being prerequisite of being interesting. That itself is very interesting. Metal.
Americanized.
Now, the grants in India are also completely connected to that. So we are belaboring that point all the time. But any time we see any metal insulator transition, the class of people that we are get very excited. Now, I can always try to tell you that as soon as you have phase transition, it can be made to put to use as a sensor and many other things. But there is no such attempt going on. Nobody sees an obvious niche application for the nickelates, but it poses a challenge for understanding. But any phase transition can be a sensor material. If I have to write my project proposal today and define, I'll write a paragraph. But in reality, I do not think I know of any obvious application at this stage.
Yeah. So.
I hear it.
Okay.
Yeah.
Yeah, Didi. So could you clarify, delta effective? So it includes the hybridization.
It includes, no. Delta effective is defined in absence of PD hopping, but it includes PP hopping, the oxygen P bandwidth, which is the uncorrelated component. It also in principle includes a D bandwidth in absence of PD hybridization, which is essentially zero.
Okay.
So that's why the delta effective is also a well-defined quantity in the many-body sense. Okay? Because the delta is a perfectly defined quantity in many-body sense, because I know exactly when there's no hopping, what the energy is, even in presence of Coulomb interaction. And there, the oxygen P bandwidth being brought in, which has no, at least at the model level, no Coulomb interaction, delta effective remains also a well-defined quantity. But there's no PD hopping. It's always defined in absence of PD hopping.
Okay.
Arindam. There are, it's like, I mean, okay, I'll answer because I don't have any stake because I'm not working on that. So slightly frivolously, it's like medicine for cold. There are too many Hamiltonians, right? So basically, in 2024, there's another which claims it's even more complex than what we have thought so far. So they have not settled the question of what the magnetic Hamiltonian is, what the magnetic structure is. I told you that nickel 4+, which in principle should be a fully filled zero moment. People have fitted experimental data both with that kind of model, with small moment that I showed in the pictures, collinear, non-collinear. So I really don't want to walk into that because it's a quagmire there. So I really don't know. I don't think it's settled. That's my impression.
So any other question? So if not, let's thank Professor Sarma.
Thank you.